So now let's move on to radial systems. So cylindrical or spherical systems where we have heat conduction. It's still one-dimensional, steady state, and no generation. So the one dimension here is the radial direction. So if you have a pipe, heat flow is coming out the pipe radially. If you have a sphere, the same thing. So here's the heat equation for cylindrical coordinates. And like we did with a 1D plane wall situation, we want to make these simplifying assumptions to get it in the right form. So the dimensions, the angular dependence, the z dependence, the generation, and the energy storage term go away. And then we're left with this relation here. So here's our cartoon of the system that we're interested in at this point. So we have a cylinder that's hollow. So some sort of fluid could be flowing inside of the cylinder. Air could be blowing on the outside of it. And if we solve this problem under our assumptions of 1D steady state conduction with no generation, we get a temperature profile. And this is applying the boundary conditions of constant temperature at the inside of the cylinder and constant temperature at the outside of the cylinder. Applying those boundary conditions and solving our partial differential equation, or we end up with this relationship here for the temperature profile. And what should be noted here is that the temperature profile is no longer linear. So when we had a plane wall in Cartesian coordinates, we found that our temperature profile was linear given that our thermal conductivity and our area was constant. But in this situation, we have a logarithm, natural log, showing up in our temperature profile. So T as a function of R is logarithmic, not linear. And we can see that here. So this point on the plot is the inside of our cylinder, and this point is the outside. And what happens is the temperature profile moves from the inside to the outside. It bends in this logarithmic fashion. So let's think about that a little bit more. So we apply Fourier's law. We still know, because energy balance tells us this has to be true, that the heat rate, QR, is constant. We know that to be true. But why do we know that to be true? Well, we have to go back to our governing equation, and basically it's saying that thermal conductivity K times R times dt dr, the derivative of that is a constant. I'm sorry, the derivative of that is 0, so therefore it's a constant. And what is this? Well, this is Fourier's law. This is Fourier's law. This K, R, dt, dr shows up right here, where we have K times the area, and the area in this case is 2 pi RL. So here's where the R times K comes from, and then dt, dr. So 2 and pi, they're constants, of course. L in this problem is a constant, but R can be changing. However, because that R shows up in this partial differential equation, multiplying our dt dr, our heat rate is by definition constant. But that doesn't mean the heat flux is constant. So the heat flux, being the heat rate divided by the area, in fact is not constant in this case. It's a function of radial position. It's a function of R. And you can even see that. You can see that in this plot of the temperature distribution, where at the beginning, the inside of our hollow cylinder, this line is steep. And as you approach the outside of the cylinder wall, this temperature distribution starts to flatten out a little bit. So that's the logarithmic relationship. But the way you can interpret that in terms of heat transfer is that when you have a large or a steep temperature gradient, there's a higher heat flux in this situation. If it's a more shallow or closer to horizontal temperature distribution, then the heat flux drops. So why is that the case? Well, going back here, if the heat rate is constant and if R is increasing as you go out towards the outside walls of the cylinder, then that's going to increase the area over which this heat rate occurs. So the heat flux will be dropping. So an important distinction between conduction in 1D Cartesian coordinates and conduction in radial coordinates is that in both situations the heat rate is constant. But in Cartesian coordinates, the heat rate and heat flux are constant. But in radial coordinates, the heat flux is no longer constant. Heat flux depends on position R. So carrying this a little further, if we take our temperature distribution and we put it into Fourier's law, then we can solve for our heat rate in terms of our temperature and our radius, or the two radii that are important there. And then what we get from that is we get a conductive resistance. So now we have this conductive resistance, same type of conductive resistance that we derived for 1D plane wall or Cartesian coordinate conduction. But now this is for the cylindrical coordinate system. And like I said before, it's different because the temperature profile is not linear, it's logarithmic. And it shows up here in this resistance. So if you have a problem where it's cylindrical coordinate system, you can't take the conductive resistance for 1D, the L over Ka, and apply it. It doesn't work here. The one that works here is the one that's specific for radial conduction, where a logarithm shows up in the numerator, and then your thermal conductivity, just like the other one, shows up in the denominator. An interesting point here is that the units here are K over watts. And if we were to take this L and take it over here, then we would have a resistance per unit length. So we would have a K times meter over watts being our units. But in the radial system, or the cylindrical coordinate system, we cannot put our resistance in terms of specific or area specific resistance, which is K times meter squared over watts. And the reason we can't do that is because that area is changing, or that radius is changing. We can make it length specific because the length is the same for all of the radius, the different radii that we see along the problem. But we can't make it area specific because the radius is changing in that situation. So something important to note.